Good morning, everyone. My name is Osh Ogabi. I am the founder CEO of Koniku. The technology I want to talk to you about today, I have been working on this for the last 16 or 17 years of my life, give or take. So, I want to start with this, this very constrained problem. Let's say it like this. How many of you in this room know that a human being is capable of discriminating nearly 1 trillion smells? That's 1 trillion. Now, the reason why that is the case will become apparent to you soon, because when it comes to smell, we live in a hyperdimensional space. So a space that is essentially bounded by 400 receptors. The interesting thing is, even though it's our only sense that connects directly to our amygdala, that has a direct line to our emotional response, there is no technology right now that can compose smell, digitally create it, and replay it back. That technology simply doesn't exist. Just to give you an idea of how we interact with our senses. So with the audiovisual industry, so when you're talking about essentially vision and sound, it wasn't always the case that everywhere you go, you have a smartphone or you have a screen. This is something that essentially began about 120 years ago. And from those two industries, we have been able to essentially create a $2 trillion industry. So, which begs the question, so why exactly did we fail at smell? Why is that such a very difficult problem to solve? So let's go a little bit into the science of how smell is done. So on the screen there, you see the picture of a dog. A dog's nose has essentially evolved to solve two problems. The first problem is breathing. That part is easy enough. You take in air, yes, and if it powers the cells in your body. However, the second function that the dog's nose does is that of sample collection. So you have a path in the nose where the air goes. It goes to the back of the olfactory epithelium. And you have essentially particles of smell, volatile organic compounds, if you will. And these volatile organic compounds, they bind to GPCRs. So these are tiny proteins that are on the surface of olfactory sensory neurons. The interesting thing is, in this case, you could say that the dog's nose extends all the way to the extremities, just the same way that your brain extends to your peripheral nervous system. So you have the particles binding to the GPCRs, and the olfactory sensory neurons there, they generate an action potential. And this action potential is what is then transferred to your brain to tell you you're smelling something, or in this case of a dog, to differentiate between the smell of an explosive like TATP, for instance, or bacon, or even cancer. Because dogs have been known to do all of those. So what we do here is not a simulation of the real thing. It's not an emulation in any way. We actually take brain cells, we genetically modify these brain cells to express GPCRs. Okay? So what this GPCR does essentially, it binds to the particles from the outside, even in our cell type. And inside the cell, you have an amplification. Inside the brain cells, you have an amplification of the signal. Okay? And then the question is, that signal or the response of the cell, how do we read that response from the cell? And that's where the neuroelectronic interfacing comes in. Okay? So the way to look at it is, normally you would have a circuit on solid state. So you have a transistor, you have capacitors, and other circuit elements. In this case, you have a DNA that encodes for any function that you want in the cell. Once you find that DNA, you can package that DNA in a viral particle, for instance, and you can deliver that DNA to the cell. And the cell can reprogram itself. And you can build whatever kind of exotic functions you want in the cell. In this case, we want to detect TATP. Why do we want to detect TATP? Because a customer has paid us a lot of money to do so. Yeah? So here, what I want to show you is, so you have a natural pathway, and you have the conical pathway. Now, in the case of a dog detecting TATP, for instance, when I leave this place now, I'm going to go to the airport, and I will probably get selected for randomly for further checks. But what is going to happen in that process is this. You will bring a dog around, and this dog will take about 20 seconds to just pre-screen me, right? Just like I explained to you earlier. But that wait time is a little bit too long. So nature takes a little bit too long to do that detection. So in this case, we have genetically modified our brain cells to respond even faster than what you would get in a natural state. So the natural pathway, you would have a flash of TATP. TATP it's an explosive. The reason why we're going for TATP is because, I mean, if you go to the internet and you buy bleach and what have you, you can easily synthesize TATP. It's quite straightforward to do. That's why it's the explosive of choice for terrorists. Okay? So what you're going to see is that the conical pathway, what we have designed, we can get it to respond in under 3 seconds. Okay? In comparison to what exists. And the reason why we're able to do that is because we're able to genetically deliver the right genetic material to the cell to produce what we want. So, see, it's too fast. Yes, I will run through that again. So the natural pathway, you see, the natural pathway gradually rises, whereas the mutant pathway or the conical pathway responds much faster. We have focused on this problem because it's a nicely bounded problem. So it's a nicely bounded problem that we can immediately generate revenue for, and we can show that the device works. So in this next image, you see the same cell, and the question now is, what is the technology that actually interfaces with the brain cells? Okay, I have told you about the GPCRs and how they bind to the particle. I have told you about how you modify the pathway inside and how you can make that better. So we can increase the time, we can decrease the time from 20 to 40 seconds. We can decrease that to under 3 seconds by synthetic pathway. But the next question is now, how do you record from the cells? How do you pick up that signal? There are 2 technologies to do this. Both technologies we have some patents for. The first technology is to essentially have a little gold electrode that is like a microphone. So we cover the gold electrode with synthetic DNA as well, or you can cover it with other proteins, such that the brain cells or the cells think that that other artificial substrate is another cell. So they tend to form a synaptic junction with it from which you can record. Or you can deliver a viral particle to the cell. You can deliver a GCAM7 to the cell, for instance, and every time the cell gets a response from the outside world, you can read the excited states optically, and both technologies we have. So what you see on the bottom right-hand corner is the actual time series signal that you get from the cell every time it comes across a particle. So on the bottom left-hand side, you see the neuron that is being colored in green. In this case, we deliver GFP to it. And every time the cell comes across a particle, it increases in spike in frequency. And on the top right-hand corner, you see the electrodes that we develop, which can actually give you patch clamp quality signal. So normally, when you want to do those recordings, it takes you anywhere from a week to 2 to do that. But we can do that at scale. And also here, with the optical system, we can show you here a dose response curve that shows you that with different gradations of TATP that is applied to this device, you can do the detection. And what we show in this image, is that we can detect in 1 part per billion. Okay. The natural state of the TATP receptor can do something around 100 parts per billion, and we're able to reduce that to 1 part per billion by doing some protein engineering. So this is what the test, an example test rig looks like. So on the white part there is the bead that has all the cells in there. Okay, that's the white part there. Underneath, we have a chip, an FPGA chip, that processes all the signals. And we also have essentially a small cell phone battery that powers it. This gives you a better idea of what it looks like. It's currently run by a Xilinx Spartan 6 FPGA chip. It has a microfluidic consumable chip on it. And the white part you see there, that is the semi-permeable membrane that covers the entire structure. So you have a cell There's a semi-permeable membrane on it, and underneath you can pick out the signal. The semi-permeable membrane essentially allows this living machine, it allows it to breathe. Remember, these are living cells, so they have to be encased in a media, okay? And this media is constantly perfused on the cells. But you have a membrane where the particles from outside essentially come in, and the cells are able to, you're able to get a response from the cell. And this is the 3-layered microfluidic device, a cassette, that you can essentially replace after every month. Currently, we want to have this consumable replaced after 1 month because it fits our business model. And this is what the device... I didn't think you guys... Okay. So this is what the device, we call it the Coney Cube. This is what the prototype looks like. So there's, on the right-hand side, you see the neuron food. There is a control electronics inside, and here you see the perfusion system put together. But this is the prototype device. You will see what the ship-ready device looks like. And I thought I'd show you a small video of our guys while we're putting this together.
Also, quickly review the other soldering
he's our
because you might
engineer.
have to do it.
Currently, we can make 100 of these devices per month. We have capacity to make 100 of these devices per month. The consumables, we currently have the capacity to make 10,000 of them per week. Our goal is that by the end of the next year, we can make 10,000 of the base devices per month. We currently signed a bunch of manufacturing partnerships in Germany that I cannot talk about at the moment, but our goal is we have to build a foundry of sorts, but yeah, I will talk about that later. So here's the device being exposed to TATP, and you can see after a while, you will see, not after a while, after 10 seconds, you will see the lights for the detection. And currently, we can do this detection at a distance of about 20 centimeters. Our goal is to have it a larger distance by being able to sample the air properly. We haven't focused so much on that. We have more focused on the synthetic biology side and the electronics bit. Okay. So this is what the final device looks like. It's a bio-inspired device. We pay homage here to the jellyfish because it was the first system to essentially have a neural network. It has a breathing port that allows it to essentially keep the airflow stable for a little while. One of our first use cases is the airport use case. And in this case, that means you can have these devices, we can have these devices essentially embedded in walls, if you will, that when somebody comes through an airport, you can actually screen the person in a non-contact way. That logo wasn't supposed to be there, that's why I had to skip through that. One of the other verticals that I'm very excited about is taste. Not a lot of people know it, but taste is actually 80% of your smell. So the question here is, what does the digital copy of Coke look like? What does the digital copy of a Downy smell looks like? What we can do in this case is we can essentially replicate all the receptor repertoire that a person has in the nose. We can replicate it on the chip, and you can present any sample that you want. You can present it to our chip, and you will get essentially a digital copy of it. So we can produce what the digital fingerprint of Coke looks like. One of our earliest customers in this case was P&G, and P&G had a problem of refining a $500 million revenue product. What this product is when you go into the bathroom, you realize that it has a very strong chemical smell. And what P&G is after is when you go into the bathroom, that it doesn't have this strong chemical smell, but it doesn't have the smell of a bathroom either. It just smells of nothing. And the way to do that is to actually figure out which receptors are triggered when you go into the bathroom. And this is a problem we're able to give a solid help for P&G on this. Okay? By far, the largest vertical that interests me is health. The idea that as you're sitting in this room, from your breath alone, you have more than 1,000 different VOCs that are coming out from your nose. And these VOCs, they are directly linked to your state of health. Okay? So for liver cirrhosis, for instance, just being able to detect 11 VOCs in your breath will tell you if you have liver cirrhosis. Or in the case of pneumonia, you have 12 VOCs that will tell you if you have pneumonia. Or for the 6 most common type of bacterial infections, you need just 4 VOCs to be able to detect that. By the end of next year, our goal is to have a chip that has more than 100,000 different channels. So you can have this chip everywhere in people's homes, for instance, and you'll be able to diagnose people's breath. But that's the early days yet. The reason why that is exciting is because if you look at the healthcare spending globally today, if you look at China alone, in the next 30 years, the cost of healthcare in that country is going to increase by 700%, which is quite significant. And we're not the first ones to realize this. There was a clinical trial in Technion the other day that were able to show that you have, for different cancers, you have essentially different VOCs. So they form a kind of fingerprint, if you will. We are addressing a $250 billion market from diagnostics, industrial, consumer packaged goods, and what have you. We have been around since about 2015, and so far we have raised about $5 million. So where we are now is we can make, like I said, 10,000 consumable devices a week, and we have capacity. This was as of Q3 of last year. Now we have capacity to make 100 of these devices in a month. But that's just the beginning. For us, the problem that I just talked about is a well-bounded problem, right? For the future, what do we want to do? For the future, what does neural interfacing look like? This is a bad comparison, but it gives you an idea that when you compare just how densely neural systems are packed in comparison to silicon systems, you find that these numbers are really quite large. We made the numbers that to copy 1 centimeter cube of gray matter at full density, you would need to build a chip about the size of a basketball court. And that's because neurons are able to layer things quite efficiently. So these are some of the early designs that some of our guys have done. So here you see there are 3 reaggregates, essentially. So you have 3 neural cores, if you will. And we're able to essentially create a circuit where the neurons are able to find themselves and make connections. Also here, there are toy examples that we're able to make these neurons grow in 3 dimensions. So what I told you about is at first was modifying the receptor, modifying the inside of the cell, and being able to get a response from it. What we are showing here is on the macro scale. We are not only able to modify the cells now, we're able to build full-on circuits out of it. We've been able to show the proof of principle that you can have different centers, design whatever connections you want from them, and be able to read from them. Even on the bottom right-hand, on the bottom here in the middle, you see that we're able to essentially replicate the blood vessels in the brain. So we take a mouse, we scan the brain of the mouse, we take the blood vessels, and we essentially, so the one that is shown in grayscale, and the one that you have in green, we're able to do that in hydrogel. So we're able to recreate the blood vessels in the hydrogel and put cells there at the same time. Interestingly, one of the first problems that we wanted to solve with this was to show that you can train this neural network. That there is this phenomenon in neuroscience that you say neurons that fire together wire together. So what we did here was to deliver a stimulation to one center and record from another center. Okay, and with this we're able to show that we can modify the membrane potentials after training for 60 seconds, and we're able to show that the training does hold for 60 seconds. But of course, that needs to be increased a lot longer than 60 seconds. But for us, this is a kind of mini R&D and proof of principle of what we could do there. To make this into a market-ready system will still take, there's a fair amount of market research or market fitting that needs to be done. So this is one example of one of those chips. Again, you see it center. So this is looking at the top, and you can see the different connections that exist on the different layers. I think that's it for me.
do you get the brain cells?
We currently get the cells from mice. So we have a stock stem cell population, and you can, if you start with a handful of stem cells, you can essentially make a house of cells if you want. So that's pretty straightforward. Yeah.
I know you have revenue right now.
Yes.
And some pilots. Where are you at in terms of commercialization, having this in the field, doing stuff?
By the end of this year, we start the first in-field pilots this year.
Can you say where that will be and what the application will be?
For security, for sure. Yes. By far our largest, it's security and defense, because people are interested in explosives, they're interested in weapons of mass destruction, and they're interested in contrabands. So by the end of this year, we would have our first on-the-field deployment. But over the last 3.5 years, internally, we have had a lot of milestones that we've crossed with really huge clients. And this has been, for us as a company, it's been a very, very good forcing function in helping us not just work with corporates, but us essentially know where to drive the product and what people are actually interested in.
And what is the fidelity in terms of the range? Do I have to walk into a closet-sized space in order for you to detect if I'm wearing a bomb vest? Or if we had one in this room, would we know who has the bomb vest on?
Great. At the beginning, so there's when you have this kind of short talks, people get the impression that it's going to be like I'm standing here and there's a device in the other room and it can detect it. That's not going to happen, at least not yet. So right now, there are two things that you need to solve for. You need to make the receptors a lot better than what they are, and you need to be able to control the airflow to an extent. Okay?
Got it.
So currently, without controlling for airflow, we can do about 20 centimeters. We think we can increase that to 1 meter, 2 meters, even without much airflow. But beyond that, you need to strategically place these devices and be able to modify airflow to an extent.
So we might see an experience where you walk through a glass box on the way to the
you
airport.
just walk through a hallway. So
Yeah.
one of the pilots that we're deploying around the Bay Area in an airport is a hallway. It's for insider threat detection. So currently, the bigger threat that people are thinking of more now is that you have a situation where, the passengers are scanned and most of the attackers there, they are opportunistic. But for the insider threat, you have a lot of trusted people that should not be trusted, right?
Right. People who work at restaurants or baggages or security,
exactly.
they could be flipped pretty easy.
Exactly. And what the airports want to do now is they want to have 100% screening there. And that's where we're starting from. And it's also an unregulated space, right? Because your client there is not the government. If something does go wrong, the government will come after you. But they are not your client. They are not incentivized to watch that side.
They're not
right?
the responsible party.
Exactly. So these guys pay for it, and you have a hallway that people can walk through, and you can essentially collect those compounds.
Okay, let's take a final question.
On the topic of security applications, I'm curious, what's your iteration time on getting a cell culture up? And then are you worried about, you could imagine for an explosive compound modifying the molecule so that it reduces binding affinity but still has the potency? How would you deal with that?
That's a very good question. So your adversary in this case, right, so if a lot of PhD students want to do a lot of damage to this planet, they could. Just so that we're clear on that. I don't know why that's actually, so if you wanted to really make a lot of damages, you could do that. If you know the receptor that you're after, that's why we don't share receptor codes, for instance. If you know what you're doing, you could design a molecule that would evade detection. Yes, you could do that. But it's essentially it's an expensive operation to do that. So you would need a high throughput screening system and so on and so forth. Essentially, you would become a pharma company. But these are not our adversaries, right? The guys that we're after are guys that their budget is what? At most $100 million, right? With our technology, well, we can get ahead of that. But for state actors, right? It's a whole new level, I think. So yes, you can design molecules if you have the right computational tools and you have the right equipment. But the FBI should probably come after you if you're buying such things. Yes.